All right, so this is the first part of Unit 4, which is actually on energy and work, and it's mainly on Chapter 10 of your textbook. So the first thing we're going to look at is just kind of the basics of energy. So every system in nature has a quantity called the total energy, and energy is just something used to make things either move or stay in a position. And all systems have a bunch of different types of energies. The total energy in the system is the sum of all the energy in there. Okay, so total energy, sum of energy, kind of like we looked at net force. So like total energy here. Some important energies, and we're going to talk about these in different stages this year. So we have kinetic energy, which is energy of motion. The more you move, the more kinetic energy you have. Gravitational potential energy is stored energy associated with the height above the ground. So the higher you go, the more potential you have to go back down to the ground. Springs or other elastics like a rubber band have what's called an elastic or spring potential energy. Thermal energy is kinetic and potential energy in the molecules. Energy stored between bonds and molecules are chemical energy. And the nucleus of an atom has energy stored in it called nuclear energy. So make sure you look over these, understand the different types, and we're going to talk about most of these as we go along here. All right, so energy can be transformed in a system into other kinds of energies. So kinetic can become potential, can become electrochemical, can become heat, but that total amount of energy remains constant. It can just change forms. All right, so if we look at this, like the one on the left, the weightlifter converts chemical energy to gravitational potential energy above as she lifts up the barbell. The diver, elastic potential in that spring is converted to kinetic energy to make it move. And then as the diver goes up in the air, some of that kinetic energy becomes potential energy. And then as it comes back down, the potential is converted back to kinetic. Okay, so two different things with energies here. Energy can be transferred between a system and its environment through what's called work or heat. Work is just a transfer of energy, okay, by making it move. You apply a force over a distance to make something move, you do work. Then if you just have energy between temperature changes, that's heat. So when something cools down or heats up, that's heat transfer. So work transfer is when something moves. Heat energy is when energy transfers to change the temperature. Okay, so the athlete does work by moving the shot put. Your hand does work to get the match going. And the boy, if he pulls back the slingshot, does work on the slingshot to make it move and increasing the elastic potential energy. So giving it energy does work. Okay, so work, there's something called the work energy equation or the work energy theorem. That the change in energy, which is change in all the different types of energy, is equal to the work done. And if you put energy into the system, you say that the work is done to the system. If energy is released, its work is done by the system onto the environment. Okay. And if no energy is transferred into or out of a system, it's called an isolated system. So again, you add work. Work is done to the system. The system does work onto the environment. The work is done by the system, and it has actually a decrease in energy. Okay. An isolated system where no energy is coming in or going out, the total energy inside of it remains constant. It just changes different forms, but the total energy is constant in an isolated system where no energy can come in or out. All right, so talked a little bit about work, but what is it? Okay, work is done to make something move, to change energy, okay? So work is done on a system by an external force. You have to add energy into the system, okay? So the wind, in this case with this parasailer here, the wind adds energy to the sails, which increases the kinetic energy. Kinetic energy is energy of motion. Okay, so work, the main equation for work is force times a distance. Work done by a constant force in the direction of a displacement. The unit of work is a joule, which is also a Newton meter. So newtons of force times meters of distance gets you a joule of work. Also a joules of energy. Okay, so the more force you apply, the more work you do. The farther you make something go, the more work you do. All right, so we have this person pushing a heavy crate 3 meters across the floor at a constant speed. She has to apply a constant horizontal force. How much work does she do on the system? Okay, so she applies a 70 Newton force over a 30 meter distance. We're going to find the work done. So the work done is force times distance. 70 newtons times 3 meters is 210 joules. Okay, so like it says here, by pushing on the crate, Sarah increases its kinetic energy, so then the work done is positive. Now to do negative work, you're actually pushing against the direction of motion to make it slow down. Okay. Now, if we're looking at work done not horizontal, so like this one, work was done in the same direction of motion. If work is done at an angle, then it's like tension on a string. So the work done, if the object's going horizontal, the work done, if our force applied is at an angle, the work done is actually just the x component of this force. That's why they say it's force times distance times the cosine of the angle here. It's the horizontal component of this work. The work is the horizontal component of the force times the distance that it travels. Okay. So again, we have this situation. Horizontal forces, work is just force times distance because you have no angle. You increase the angle, work is force times distance times the cosine of theta. So if you apply a force perpendicular to the motion, you're not really doing work in the direction of the object's motion, so you do no work there. No work is done on the system if you pull it up while it's sliding or you push it down, straight down while it's sliding perpendicular. No work is done because the cosine of 90 is 0. So force times distance times 0 is 0. And then if you apply to the opposite direction of motion, you actually do negative work on the system. So if you pull against the direction that something's traveling, you're doing negative work. Okay. All right. So again, if you pull in the opposite direction, you do negative work. All right, so sample problem here. So pulling a suitcase at the airport, the tension on the strap is 20 newtons. How much work does the tension do if the suitcase is pulled 100 meters at a constant speed? Okay, so that your tension is 20 newtons. Your angle is 45 degrees. You want to find the work done, which means we need to find the horizontal component of this force. To do that, the tension is 20 newtons. The distance is 100 meters. But your tension times the cosine of theta gets you the horizontal component here. So tension of 20 newtons times the cosine of 45 gets you that force. So 20 newtons times the cosine of 45 gets you the horizontal component, which is the force actually doing the work, times 100 meters gets you 1,400 joules of work. Now notice it says here the tension is needed to do work on the suitcase, even though the suitcase is traveling at a constant speed to overcome friction. So the work done is positive. Okay, the work done goes entirely into increasing heat energy of the suitcase and the floor. Okay, you increase the heat energy when you have that friction, because of friction there. All right. Forces do no work if various situations here. If there's no motion, the force is perpendicular to displacement. The part of the object on which the force acts undergoes no displacement, so it doesn't move. If the part that is exerting the force doesn't move, there is no work done on the object. Okay? It's like if the lady actually pushes on the wall, she's actually doing no work on the wall because the wall doesn't move. All right. Now, the two different types of energy that are the main components for this video are kinetic and potential energy. So kinetic energy is simply the energy of motion. Okay? And there's two different types, linear and rotating kinetic energy. Okay? And so translational is just linear kinetic energy. And the formula for linear kinetic energy is 1/2 mv squared. Okay, so mass, 1/2 mass times your velocity squared is your kinetic energy. Rotation, spinning kinetic energy, is what's called the moment of inertia. So that's kind of like how easy or hard it is to slow down an object once it starts to spin, times its angular velocity squared. So basically the mass of an object, when it goes from linear to rotational, is replaced by this moment of inertia, because mass kind of leads to inertia anyway, how hard it is to get an object moving. And then you're looking at speeds. So straight line, it's just v. When something spins, its rotational rate is its rotational speed, 2 pi r divided by your period. Okay. For most of what we're going to do in this section, we're going to look at the 1/2 mv squared. We will look at the 1/2 moment of inertia angular speed squared later on. So if you think about this, if you double the mass and the velocity remains constant, you double the kinetic energy. If you double the velocity but the mass remains constant, you're actually going to quadruple the kinetic energy. Okay. So like it says here, rotational kinetic energy is a way of expressing the sum of kinetic energy of all parts of something that rotates, like this windmill. All right. So with this bobsled, it has a mass of 390 kilograms. Starting from S, the two racers push the sled for the first 50 meters with a net force of 270 newtons. We want to figure out the sled's speed at the end of 50 meters. So, So, we're not going to look at change in thermal energy. So we're going to look at what's called the work energy theorem to look at change in kinetic energy is the work done. So the sled's final kinetic energy and then its final speed by finding the work done by the racers as they push the sled. So we have an initial velocity of 0, okay, but we know with this that a force is applied over a distance and we know a mass. So with this, we know the mass of 390 kilograms. We know the distance that it moves is 50 meters. We know the 270 Newton force applied, and we know the initial velocity is 0. Okay? So the work done by the pushes increases the sled's kinetic energy. So we need to find that final kinetic energy. So to do this, since work is change in kinetic energy, Okay, so that means kinetic energy final minus kinetic energy initial is work. So ultimately, that means kinetic energy final is going to be kinetic energy plus the work done. So kinetic energy final is 1/2 mv final squared. Kinetic energy initial is 1/2 mv initial squared. Work is force times distance. Okay, so you have an initial velocity of 0, so we have no initial kinetic energy. So for this particular problem, it boils down to 1/2 mv squared is equal to force times distance. Because we're looking for final speed here, we're going to multiply both sides by 2, so you get 2fd equals mv final squared, and divide both sides by m, and you're going to get down here. Vf is equal to the square root of 2 times force times distance divided by mass. So the force is 270, the distance is 50 meters, the mass is 390. So 2 times 270 times 50 divided by 390, take the square root of that, and you get a final speed to be 8.3 meters. Now, if how I did this confuses you, just go back and read it, look over what happened here, and ask questions about it in class. Okay, the other type of energy with the math, with this mechanical energy, is potential energy. So we looked at kinetic energy, which is energy of motion. Potential energy is stored energy. Okay, the main one we're going to look at here is what's called gravitational potential energy. Energy due to how high you are above the ground. Okay. So the higher you go up, you have to do work to lift the book up. You're actually building up energy as you lift it up. Okay, its gravitational potential energy is increasing as it goes up. So again, the change in potential energy is proportional to how high you go up. Gravitational potential energy, which is UG, is equal to mass times gravity times your height. So the higher you go, the more potential energy you have. Okay. So like in this case, if we have this hiker person here, the higher it goes, the more gravitational potential energy we have. And again, it depends only on the height of the object and the object's mass. Not how far you travel, just your vertical distance from whatever your 0 point is. Okay, so like this climber here, it doesn't matter how he gets to the top. At the top, he's going to have the same amount of potential energy whether he took the not so steep way for path A or the steep path B. The other type of potential energy is spring energy. Okay, spring potential, basically you squish it or you stretch it out, and it's the potential to go back to its normal. Okay, and you looked at Hooke's law. Okay, that force is equal to spring constant times your displacement. And that's the other type of elastic potential. That's the elastic potential energy. It's that displacement times your distance is that force that's applying. And then you can look at the elastic potential energy of your spring. And that, instead of like 1/2 mv squared, potential energy, elastic potential energy is 1/2 kx squared. The stored energy when you displace, you know a spring constant, you know the displacement, you can figure how much energy, if you're squishing it, how much energy is stored. Or when you're stretching it, how much energy is actually put into it to make it go, when you let it goes back to normal. Okay. All right, so we're going to look at this for a second, for this practice problem. So the archer pulls back the string on her bow a distance of 70 centimeters from the resting position. To hold it there, it takes a force of 140 newtons. How much elastic potential energy is stored in the bow? So the bow has an elastic material, so we're going to use Hooke's law. okay, to figure out the force. Okay, we can use the force required to hold the string and the distance it's pulled back to find the spring constant. Then you can use that to figure out the elastic potential energy. So, from Hooke's law, spring constant is F over X. F is 140 newtons. X is 0.7 meters. So 140 divided by 0.7 is 200 newton meters. So that's your K. So when you put the K in the elastic potential equation, you know the displacement. Now you know the spring constant. So 0.7 squared times 200 newtons per meter, and take a half of that, and you get 49 joules. Okay. And if you look in your book, kinetic energy of 100 mile an hour fastball is about 150 joules. So 49 joules is about half as fast. Okay. So that's your introduction on work, which is force needed to make an object move, kinetic energy, which is energy of motion, and potential energy, which is energy of a position. The questions that you have on this, please put on the bottom of the Google form, and we'll take care of those in class. And we will see you in class.